Alright, hello everyone, welcome back to 3 Deviations. In this video, we are going to be covering the inverse trigonometric functions and how we are going to be differentiating these inverse trigonometric functions. As you may have guessed, to succeed in this topic, you are going to need to know about trigonometry, and more specifically, the inverse trigonometric functions, and you will also need to know about differentiation. We're going to be making use of implicit differentiation today, mostly. Alright, so let's get started. Let's just start with defining the inverse trigonometric functions, right? So how an inverse function works is if I plug in a domain, I will get a range, and then if I plug that range into the inverse function, I will get back the domain. That's exactly how it works with these trig functions. If I plug in theta, I'll get x. And then if I plug in x to the inverse function, I'll get theta. And this is how it works for the rest of the inverse functions. So we've got sine inverse, cosine inverse, tangent inverse, cosecant inverse, and secant inverse and cotangent inverse. And you can call these inverse sine, or you could call it arc sine. I really don't care, but there are a lot of ways to name these different functions that we have. So earlier in the video, I said that we were going to be doing some implicit differentiation. Let's get back to that. So why does implicit differentiation come back here? So let's just go back to the notion of an inverse function, right? So I'm going to try to draw an inverse function here. More specifically, the inverse sine function. So if that is our graph, and we're going to have sine kind of looking like this. Try to draw a good sine wave. Alright, and we know our bounds. We're going to have pi over 2, and we are going to have negative pi over 2, and then pi and negative pi for our other maximums and zeros. And if you may have noticed what our inverse function is, it's going to be reflected across the line y equals x, and we're going to get a function that looks something like this. Or not a function. This one will not be a function because it doesn't pass the vertical line test, if you may have noticed. So we have a relation here. We have a sine wave about the y-axis. So what we need to do is we need to restrict our domain from negative pi over 2 here to pi over 2 here. Then that just this stuff above here gets canceled out, and that stuff below here gets canceled out because we're restricting that domain. So what we end up with is we have a function here. So that's our new sine wave, our new inverse sine function. And we could differentiate that, but what's going to be really nice is implicit differentiation, because then we could differentiate this whole thing and then add back our domain restriction. So let's do that. Let's try to differentiate the inverse sine function. So what we're going to do first is we're just going to do some rewriting. So we have y equals sine minus 1 of x. So what we're going to do, we're going to rewrite this as x equals sine of y, because that's what the inverse function is. And we are going to restrict our domain here from negative pi over 2 to pi over 2. And now what we are going to do is we're going to differentiate both sides with respect to x. So we're going to take the derivative of sine of y with respect to x, and that's going to be equal to the derivative of x with respect to x. So we can rewrite this as the cosine of y dy dx is equal to 1, because if we take the derivative of x, we get 1. And now we can do some more rewriting. So we're going to get cosine of y is equal to 1. So we're going to rewrite cosine of y, and we are going to get cosine of y is equal to 1, the square root of 1 minus the sine squared of y. And we already defined sine of y here, and that's equal to x. So we're going to rewrite this as the square root of 1 minus x squared. And now we have, now we just need to divide by 1 the square root of 1 minus x squared in order to isolate our dy dx. Then we will get the derivative of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. Sorry, we've got to remember that square root in there. All right, so now let's try for the tangent. We're not going to do all the functions. We're just going to do sine and tangent. So we're going to do something very similar. We're going to rewrite the inverse tangent as x equals the tangent of y. And again, we're going to differentiate both sides with respect to x. So we'll take tangent of y with respect to x equals the derivative of x with respect to x. Once again, we will get the secant squared of y dy dx is equal to 1. The derivative of x is 1, and the derivative of tangent of y with respect to x is secant squared y dy dx. Now, we are going to be able to rewrite this, and we will get dy dx is equal to 1 over the secant squared of y, which could be rewritten as 1 over the 1 plus the tangent squared of y. And because we defined x up here as the tangent of y, we can rewrite that as 1 over 1 plus x squared, giving us a final answer of the derivative of the inverse tangent of x is equal to 1 over 1 plus x squared. All right, so that is our derivative of the inverse tangent. Now, I'm just going to throw all of them out on the board. So we already talked about the derivative of the inverse sine, and that was 1 over the square root of 1 minus x squared. And we also have the derivative of the inverse cosine, which is negative 1 over the square root of 1 minus x squared. Be careful of that negative sign. And now the derivative of the inverse tangent is 1 over 1 plus x squared. We already talked about that. And the derivative of the cosecant, the inverse cosecant, is negative 1 over x times the square root of x squared minus 1. Be careful of that negative sign again, right there. And furthermore, we have the derivative of the inverse secant is 1 over x times the square root of x squared minus 1. And finally, we have the derivative of the cotangent, the inverse cotangent here. And again, negative sign. So that will be 1 over 1 plus x, negative 1 over 1 plus x squared. All right, so that is the derivatives of the inverse trigonometric functions. While these aren't going to be terribly important in the first half of calculus, similar to the hyperbolic function, the inverse hyperbolic functions, these are going to be very helpful in the next part of calculus. So that is our video. We will be back next time to briefly go over the concept of a differential, and we will talk about population growth. And after that, we will be right into our next unit of the applications of differential calculus. Thank you for watching. See you later.